Hi students, today we are going to discuss about in 11th mathematics the topic is relations. Okay, relations. So simply we want to say relations is a subset of the Cartesian product. Okay, Cartesian product means A is a non-empty set. A is a non-empty set and B is another set that is also a non-empty set. Suppose A contains two elements A, B. B contains the elements 1, 2. Now the Cartesian product A cross B is nothing but A, 1, A, 2, B, 1, B, 2. This is called as Cartesian product of the set A and B. Now the relations are called as subset of the Cartesian product. Subset of the Cartesian product. Here, whether we can take all the four pairs or else any two pairs or else any one pair, whatever it is we can take, the subset is called as relation. Here we can define or the relation is equal to A, 1, B, 2. Here the relation is A, 1. What is the meaning for A, 1 means? A is related with 1. A is related with 1. The next relation B, 2. How do you read this means? B is related with 2. B is related with 2. And in day-to-day life, how to use the relationships means like as father, son. So one relationship. Family, one relationship. Okay. Like that, here we are going to discuss about this topic, relation. Okay. By the definition of relations, how do we define means? Listen here. Here we are taken two sets. One is A and one is B. Let A and B are any two non-empty sets. Any two non-empty sets. And R is the relation from A to B. Usually relation from the set to the set. They should be there. Okay. Here the relation R. How to read this mean? Relation R such that from the set A to the set B. Relation R from A to B is defined by R is equal to set of all pairs. Set of all pairs A, B is a pair. A, B is a pair. In this A is belongs to the first element should belongs to the first set A from the set. The second element should belongs to the second set B to the set. Okay, set of all pairs A, B. In this A belongs to A and B belongs to B. So this is nothing but subset of the Cartesian product. Okay. Now types of relations. Now relations are classified into three types. The types are called reflexive, symmetry, transitive. How it means? Let us take one non-empty set. Let us take one non-empty set. Let S is a non-empty set and R is the relation. R is the relation on S. Actually, by the definition, what is it? R is the relation from the set A to the set B. So from and to both are different set means then we should mention from the set to the set. Suppose the relations are on the set means from the set to the sets both are the same. Here we defined the relation R on the set. Yes, on set means that is from to both are the same sets now. Okay. So here reflexive means for every A belongs to S. For every A belongs to S. The pair A, should be belongs to R. The pair A, should be belongs to R. Suppose S has 5 elements. S has 5 elements. Example 1, 2, 3, 4, 5. Then 5 pairs should be there like that 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. If all the 5 pairs should be there in the relation R, then the relation R is satisfies the condition reflexive. Okay. Then the second one is symmetry. Symmetry in the sense means if this pair is existed there, then only we can go for this pair is either there or not. Suppose the pair A, B does not exist in R. The pair A, B does not exist in R. Automatically it is symmetric. Listen clearly. What is the definition here? If A, B belongs to R, if this pair exists in the relation R, then the symmetric case, reverse side, B comma A should be belongs to R. For example, one pair 1 comma 2 is belongs to R. Then how do you say this is symmetric? Means surely the pair 2 comma 1 should be exist in the relation R. Then only we can say this is symmetric. Okay. So listen clearly. Every pair with the same element. Every pair with the same element is called as reflexive. If the pair A comma B is there and the reverse pair B comma A is existed in the R, then it is called as symmetric. Then the third one, transitive. If these two pairs are existed, then only we can go for this case. If A comma B belongs to R. So what is the element in the second, in the first pair? First pair, the second element. First pair, second element. And one more pair should start from the element B. From the element B. So A comma B belongs to R and B comma C belongs to R. Then we can pair with the element A and C. So A comma C belongs to R. So if these two pairs are existed, then we should verify this pair is existed in the relation R or not. If it is existed, this is called as transitive. If it is does not existed, means it is not transitive. That's all. Okay. Then note, suppose a relation R satisfies all these three cases, reflexive, symmetric, transitive. If it satisfies all these three cases, then the name of the relation is called as equivalence relations. Equivalence relation. See here, if a relation R satisfies all the three above relations, then R is called as an equivalence relation. This is a necessary and sufficient condition for equivalence relation. All the three relations should be satisfied. We can discuss about few results in relation. In this, the first point is about relation R on the set S. Relation R on the set S. Then see that R is equal to set of all pair A comma A, where A belongs to S. So here the whole relation R consists of the pairs with the same elements. So how many elements are there in A? Those all elements we can fix with the same elements of pair here. Then the relation R is called as an equivalence relation. Then you will think about, so how do you say this is an equivalence relation? Previously you said the condition for equivalence relation is reflexive, symmetry, transitive. If all the three are satisfied, then only it is called as equivalence relation. Suppose here R is equal to 1, 1, 2, 2, 3, 3, where S contains the elements 1, 2, 3. It is an equivalence relation only. How it means? First case reflexive, the same element pair. Same element pair is called as reflexive. 1, 1, 1, 2, 2, 2, 3, 3, 3. Suppose 3, 3 is not there. 3, 3 is not there means that is not reflexive. How many elements are in the set A? That much pair should be there with the same element pair. Okay. So here 1, 1, 2, 2, 3, 3 all are there. Then it is reflexive. Then how do you verify about symmetric means? What I said previously, if A comma B is belongs to R, then only we can go for B comma A is belongs to R or not. Here can you say any pair like that different elements? Can you say any pair like that different element? Here all are the same elements. So what I said in the definition, if this is exist in R, then only we can go for this case. But actually this type of elements are not here. Then how do you verify this one? So directly we should assume the symmetry is satisfied. The symmetry is satisfied. That's all. Okay, because these types of pairs are not here, so that we are taking directly it is symmetric. So like as for transitive also, if A comma B and B comma C both are belongs to R. If A comma B, so what is the second element in the first pair? That element should be the first element in the second pair. So like the pairs are there, then only we should verify either A comma C is belongs to R or not. then only we should verify is A comma C is belongs to or not. Okay, then here, so like that different number pair is not here, different numbers pair not here. So therefore without the pair, then how do you verify this transitive or not? So directly we should take this is transitive. So the elements are same pairs, okay, or consist of the pairs with the same or consist of the pairs with the same element. It is called as equivalence relation. Okay, then next second point, if A is n of A means number of elements or else the cardinality. Cardinality means nothing but the number of elements, that's all. Okay, n of A is equal to P and n of B is equal to Q, and R is the relation from the set A to B. R is the relation from the set A to B. Then the number of relations from A to B. So A has P elements, B has Q elements. Then how many relations we can form from the set A to the set B means 2 power PQ. 2 power PQ number of relations are possible. Suppose, the third case now, if R is the relation from the set A to A, R is the relation from the set A to A. So what is the meaning? Relation R is on the set A. R is on the set A. And n of A is equal to n. N of A is equal to n. Then the number of relations, on A is 2 power n into n, like as the previous formula. Here two different sets and two different number of elements are there. Then we use it here. Here both are the same sets. Then the number of elements are also the same. Then n into n, it will be 2 power n square. And the fourth point is about relation R from the set A to the set B. So from one set A to the set B, how many reflexive relations, how many symmetric relations we can form means, these are the formula. The number of reflexive relations from the set A to the set B means 2 power n square minus n. 2 power n square minus n. The number of symmetric relations from the set A to the set B is 2 power n square plus n divided by 2. Or else, here you can take n as common outside, then n into n plus 1 by 2. So why I am giving this formula means, they can ask about 1 mark. Okay, so in 1 mark they will give if n of A is equal to 3, n of B is equal to 4, then how many number of relations possible? How many number of relations possible? Means then it is 2 power 3 into 4, 2 power 12 as I given in the second formula, okay, second result. Okay, this is, suppose here both n of A and n of B both are n, then only it is possible here. If n of A is equal to n of B is equal to 4, then how many reflexive relations are possible? Like that they can give the cardinality. Cardinality means nothing but the number of elements. Cardinality means nothing but the number of elements. They give two sets, the number of elements in the two sets, and they will ask about the number of reflexive relation. They will ask about the number of reflexive relation. Then it is 2 power n square minus 1 minus n. Then it is 16 minus 4 is equal to 2 power 12. 2 power 12 reflexive relations are possible, as you should know, otherwise you can't find it. Okay, so like as a formula you should read it. Now example 1.10 sums. Okay, the question is about check the relation R is equal to set of all pairs 1 1 2 2 3 3 etc n n defined on the set S is equal to 1 2 3 up to etc n for the three basic relations. Actually basic relation means nothing but the reflexive, symmetric, transitive. These three are the basic relation. If a relation satisfies all these three basic relation, then it is called as equivalence relation. Okay, here we are going to verify whether this relation satisfies the three conditions or not. First one, for every A belongs to S, which implies the pair A comma A is belongs to R, because here see 1 is there in the set S, then the pair 1 comma 1 is there in this relation R. The element for 2 in the set S, the pair 2 comma 2 is belongs to the relation R. The element 3 in the set S, the pair 3 comma 3 belongs to the relation R. So like as for the element n, the pair n comma n is exists in the relation R. Okay, so for all the elements in the set S, here the relation R 1 1 2 2 3 3 like this up to etc. n n. So if it is like this, surely it is reflexive. Then reflexive is true. Reflexive is true. Second case, symmetric. Actually, if A comma B, if A comma B is belongs to the relation R, then only we can verify B comma A belongs to R or not. But here, the different element pair is not here. Here, A comma B is does not belongs to R. Here we cannot find out about the different element pair. So automatically it is symmetric. Therefore, symmetric is true. Third case, here A comma B and B comma C pairs are does not exist in the relation R. Actually, if these two pairs are exist in R, then only we can verify A comma C belongs to the set R or not. If this type of pairs are not exist in R, then how do you verify it is transitive or not? It is not possible. Then automatically we can take as transitive is true. So in question they said about verify for the basic relation, but here it is satisfies the reflexive, symmetric, transitive. So as per the definition of equivalence relation, if a relation satisfies all of these three, then it is an equivalence relation. So this implies the relation R is an equivalence relation. Okay, right. The next example 1.13. Here the question is, in the set Z means integer set. Okay, define M relation N, M or N. How to read means M relation N. If M minus N is the multiple of 12, M minus N is the multiple of 12. Prove that R is an equivalence relation. Now the relation is M relation N, M comma N. The pair M comma N means the value M minus N should be a multiple of 12. It's nothing but division divided by 12. Both are the same meaning. Solution. First one, M minus M is equal to 0. Why I am taking M minus M means, I will explain, right. M minus M is equal to 0. This 0 can you write as 12 into 0 because of multiples of 12. Okay, multiples of 12. So this implies M relation M, or else M comma M it belongs to the relation. Therefore, reflexive is true. Okay, listen, why I am taking M minus M means, here the relation M comma M or N means that is nothing but M comma N. Okay, the pair M comma N means, how the pair we can assume means, the value M minus N is a multiple of 12. So here, if you want to write reflexive means, in all the pairs, same elements only should be there. So take M comma M. So according to the condition given, M minus M is equal to, that is 0 now. This 0 we can write as 12 into 0. Then it is multiple of 12 only. So if this is multiple of 12 means m comma n belongs to R. So like this, reflexive is true. That's all. Second case, if m comma n belongs to R, this implies m minus n is a multiple of is a multiple of 12, that we can write as m minus n is equal to something 12 into k, some scalar. Okay, this one we can write as n minus m is equal to minus 12k. Now how can we take this means 12 into minus k, 12 minus k. So this is also nothing but multiples of 12 only. N minus m is a multiple of 12. That is m comma n belongs to R. Therefore, that is n comma m belongs to R. Therefore, symmetric is true. Symmetric is true. Then third case, transitive. If m comma n is belongs to R, this implies m minus n is equal to something 12k, and n comma p is belongs to R, mean this subtraction value is also multiples of 12. Okay, now add these two values, m minus n plus n minus p is equal to 12k plus 12l. Here we can remove the minus n and plus n. Remaining it is m minus p. This is equal to 12 into k plus l. Later, the value k plus l we can treat as something lambda. Then it is m minus p is equal to 12 lambda. So this is nothing but m minus p is a multiple of 12. So therefore, m comma p is also belongs to R. This implies transitive is true. Transitive is true. So listen how it means. What is the condition for transitive? The pair a comma b and the pair b comma c, if both are belongs to the relation, then a comma c is also belongs to the relation, then it is transitive. Let it is a comma b and this is b comma c. Then we want to prove a comma c condition. Okay, here the condition is the subtraction value is a multiple of 12. So m comma m means belongs to R, we assumed. Then it should be the multiples of 12 only. N comma p, this is also a multiple of 12 only. Now add these two data, then you can remove the n and n. We will get m minus p is equal to 12 into k plus l. Now the value k plus l, this is one scalar, this is another scalar. Both we can add as something scalar as a lambda. M minus p is a multiple of 12. So the pair m comma p belongs to the relation R. Therefore R, it is transitive. So transitive is true. Therefore the relation R is an equivalence relation. How it is equivalent relation means, here all the three basic relations, are satisfied. So if a relation satisfies all these three relations, then it is an equivalent relation, then it is an equivalence relation. That's all. Okay students, now exercise sum. Actually few questions are like as example and exercise, both are the same sums. So you can see the example and exercise sums to match the sums which are related to one another. Okay, here I am going to discuss some few different questions only. Here Exercise 1.2, the second question. This is same as the method of example 1.11. So if you see this sum, then the sum will be easy. Otherwise, if you see that sum, this will be easy. Okay. Here, say the question that x is equal to set of the elements A, B, C, D, and the relation R is equal to set of pairs AA, BB, AC. Now, write down the minimum number of added pairs to be included to make R as reflexive, symmetric, transitive, and equivalence. Okay, so here this is one given set, and the relation R is defined on this set only. Here R is defined on x to x only. Okay, so in this relation, what are the pairs needed to be added to make these four relations are true? Here, the first case. Okay, listen. X consists of four elements A, B, C, D. So if the relation R is satisfied the condition reflexive means four pairs should be there. AA, BB, CC, DD. Okay. If four elements means four pairs should be with the same elements. Okay. But here the pair AA and BB only presented. Which are missed here? CC and DD are the missed pairs. So include the pairs CC and DD for R is reflexive. That's all. So if you include these two pairs, then R will come as reflexive. That's over. Okay. In second case, see here, symmetric. What is the condition for symmetric? If A comma B, the pair is there, then the pair B comma A should be there. We can omit about the same elements pair. Okay. So leave these two pairs. Take this one only. Here it is A comma C. Now, if C comma A is presented here, then it is symmetric. So that is the only needed pair to make the relation R as symmetric. Okay. So include the pair C comma A for R is symmetric. Okay. Third one, transitive. So what is the condition for transitive? If AB, BC both are belongs to the relation R, then we should verify for the pair A comma C. Here, for the reflexive condition only, we should check the pair AA, BB. For the condition symmetric and transitive, we should remove these pairs. Okay. Then for transitive, two pairs we needed. AB, BC we need. Here only one pair is there. A comma C. Okay. What is the condition reflexive? Transitive. What is the condition in transitive? AB, BC. What is the second element in first pair? That element should be the first element in the second pair. So like that, here C is the second point. C is the second point. Is there any pair like I started with the C? Is there any pair like I started with the C means that's not here? Okay, so this is symmetric or not? No, this is transitive only. Okay. It is transitive. Only. So here no pairs need to add for the condition transitive. By the given itself it is transitive only. Okay. Fourth one. So for equivalent relations we should need the pair which are missed for reflexive, symmetric and transitive all are. So if you add these two pairs, then it will come as reflexive, and if you add this pair, then it will come as symmetric. So these three pairs we should add for the condition equivalence relation. So include all the three pairs CC, D C comma A for R is equivalence. That's all. If you add these three pairs, then R will come as an equivalence relation. Next, fourth question. Here the question is, let P be the set of all triangles. P is a set which consists of all triangles only. Okay. In a plane, and R be the relation on P. R is the relation on the set P, as A related to B. A related to B means A is similar to B. Prove that relation R is an equivalence relation. Here the set which is we are going to take for the relation is set of all triangles only. This may be a scalar triangle, an isosceles triangle, an equilateral triangle, a right angle triangle, whatever it is consists of all triangles only. So all triangles will be there. But the relation condition is, if you are taking two triangles, okay, that should be similar to each other. Triangle A, B means nothing but triangle name only. Okay, triangle A, triangle B, triangle C, triangle D, like that. Or else triangle 1, triangle 2, triangle 3, like that only. Okay, if you are taking two triangles, that will be similar to each other. That is the condition here. Okay, the first one, if first one, every triangle is similar to the triangle itself. That is true only. Okay, every triangle is similar to itself. Every triangle is similar to itself. So A comma A belongs to R. For every A belongs to B. Therefore, reflexive is true. Second case, if A comma B is belongs to R, if A comma B belongs means triangle A is similar to triangle B, then reverse manner, can you say that triangle B is similar to triangle A or not? It is similar only. Okay, if A comma B belongs to R means this implies A is similar to B. On the other hand, we can say B is similar to A. This implies B comma A is also belongs to R. Therefore, symmetry is true. That's all. Okay. Now third case, if A comma B belongs to R, this implies A is similar to B. B comma C is belongs to R. This implies B is similar to C. So then we can say three triangles are there. Triangle A is similar to triangle B. Then triangle B is similar to triangle C. Then how can we say that triangle A is similar to triangle C or not? It is similar only. Okay. Then A is similar to C. This implies the pair A comma C is also belongs to R. Therefore, transitive is true. Transitive is true. So this implies R is an equivalence relation because it satisfies all the three basic relations. Then it is an equivalence relation. Okay. Next, sixth question. Here the question is, prove that the relation friendship. Here the relation is friendship is not an equivalence relation. not an equivalent relation. On the set of peoples in Chennai. Okay, in Chennai, too many peoples are there. Here the relation is A comma B, or else A related to B. Then how can you say that A is front to B? A is front to B. There is a relation here. By this relation, it is not an equivalence relation. That only we want to prove now. Okay. Here, first one, reflexive. Here, what is the relation? A comma B means A is front to B. Suppose now we are going to take A comma A. What is the meaning in that? A is front to A. How it is possible? Everyone is front to himself. Logically, is that correct or not? That is not possible. Okay? Every person is not a front to himself. Okay? So the pair A comma A does not belongs to here. So it is not reflexive. Okay? Every person is not a friend to himself. So therefore, A comma A is does not belongs to R. So this implies reflexive is not true. Okay, then the second case, two persons are there. This is A, this is B. Now we can say A is front to B. Okay, in the reverse case, B is front to A or not? If one person is front to another person, in the reverse part, the same person is front to the first person. That's true only. So symmetric is true here. Okay, so if A comma B belongs to R, this implies A is friend to B. So this implies we can say B is friend to A. So the pair B comma A is also exists in the relation R. Therefore it is symmetric. Symmetric is true. Then the third case, if A comma B is belongs to R, this implies A is friend to B. That is okay, that is true. Okay, then the next pair, B comma C belongs to R. This implies B is friend to C. Now listen, three persons are there, A, B, C. I am going to say these two persons are friends. That is, A is friend to B. Okay, then B is friend to C. That's okay, no problem. But there is no necessary to say A and C, first person, third person, they should be friends. That is need not. It's may or may not only. They may be friends or they may not friends. That's all. Okay. So here A comma B means A is friend to B. B comma C means B is a friend to C. Okay. Then A is a friend. A is friend to C is not true. Okay, it's not true. It's may or may not only. It's not true. It's may or may not only. Okay. They may be friends or may not. So therefore, transitive is not true. So if any one of these three relations, if any one of these three relation is failure, then automatically it is not an equivalence relation. So here reflection is not true and transitive is not true. Then how can you say this is an equivalence relation? That's not possible. Only symmetric is true, so that it is not an equivalence relation. Clear? Next, seventh question. See the question here. On the set of natural numbers, let R be the relation defined by A related to B. A related to B. If A plus B less than or equal to 6. So here the condition is we can take two natural numbers and the sum should be equal to 6 or less than 6. It cannot be more than 6. Like that pairs we can take like as 1 1, 2 2, 3 3, that is possible, but 4 4 is not possible. How it means 1 plus 1, that is 2, less than 6. 2 plus 2, it is 4, less than 6. 3 plus 3, it is 6, equal to 6. Okay. 4 plus 4, it is 8. It's greater than 6 only. So that pair is not allowed. Like that we can write any two numbers whose sum is equal to 6 or less than 6, and the condition that number should be a natural numbers. Okay. Listen. Write down the relation by listing all the pairs. So what are the pairs satisfy this condition from the natural number set? That all pairs we should write now. Then check whether it is reflexive, symmetric, transitive, equivalence. After writing the relations, the elements which are inside the relation, okay, those elements satisfy the four properties or not, that we want to verify now. Here, the first case, first of all we must write about the relation. So for the relation, the numbers from where we can take means from the natural number sets. So what are natural numbers? 1, 2, 3 up to etc. infinity. Okay. So 1 plus 1, 2. That is less than 6. That is possible. So with the value 1, you can take up to the 5. 1 1, 1 2, 1 3, 1 4, 1 5. All are possible. 1 2, 1 3, 1 4, 1 5. Right. Okay. If you take 1 6, not possible. 2 5, that also not possible. Okay, then again start with 2 1, 2 1, 2 2, 2 3, 2 4 is possible, 2 5 is not possible. Okay, then again start with 3 1, then 3 2, 3 3 over, 3 4 is not possible. Take 4 1, 4 2, 4 3 is not possible. Okay. Then 5 1, that's all. So after this it is not possible. It should be 15 numbers, 15 pairs. Check once. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 pairs. This much only possible. Okay, other pairs will fail to satisfy this condition. Right. So here the first one we want to verify whether it is reflexive or not. Reflexive or not. Okay. Here from the set to the set, both are the natural number set. Okay. So what are the elements are there in natural numbers? 1, 2, 3, 4, 5 up to etc. infinity. So for all these numbers, how can you verify the reflexive? The pairs 1, 1, 2, 2, 3, 3, 4, 4, all should be there. Okay. 1, 1 is there. 2, 2 is okay. 3, 3 is also okay. But which two are not here? 4, 4. It's not here. 5 5, the two not here. So it's not an reflexive. Okay. Here 4 comma 4. Here 4 comma 4 does not belongs to R, and 5 comma 5 is also does not belongs to R. Therefore reflexive is not true. Reflexive is not true. Second case, here we want to verify about symmetry. If AB is means BA should be there. Okay. Further we can omit about the repeating pair 1 1, 2 2, 3 3. This type of pairs we can omit. Okay. Let us see 1 2 is here, then 2 1 is also here, so it is possible. 1 3, 3 1 is true. 1 4, 4 1 symmetric is true. 1 5, 5 1 symmetric is true. 2 1, 1 2. Sir, the value 2 1 you verified for 1 2. Don't write like this. Okay, don't treat like that, because whether 1 comma 2 is an element, its symmetric is 2 comma 1. Well, coming to the turn of 2 comma 1, it is an element of the relation. Its symmetric value is 1 comma 2, that we should verify. Okay, then don't think, so I verified the value 1 comma 2 with the 2 comma 1. So after 1 comma 5, I went to 2 comma 3. Don't think like that. This is also an element. For this, what is the symmetry that we should verify here? Right. 2 3, then it is 3 2. Okay, it's possible. 2 4, 4 2, it is symmetric. 3 1, 1 3, it is symmetric. 3 2, 2 3, it is symmetric. 3 3 you can leave. 4 1, 1 4, symmetric. 4 2, 2 4, symmetric. 5 1, 1 5, symmetric. Now tell me, is this symmetric or not? Means it is symmetric only. Okay, all the pairs satisfied the condition. Here A comma B belongs to R and B comma A is also belongs to R. Therefore symmetric is true. Okay, then third case we want to verify about transitive. Simple case we can verify. Wait a minute. Take this pair and this pair. So here, if you coming in the order 1 5 5 1, then the answer 1 comma 1 it is here. Then it satisfies about the transitive. That's okay, no problem. But we should take this order. 5 1 belongs to R. 1 5 is also belongs to R. Then the pair 5 comma 5 is does not belongs to R. Okay, if one pair is not existed, that is enough case to us to say this is not transitive. Okay, if all the pairs satisfies the condition, then only it is transitive. So one pair only failure, sir. Okay, there is enough case to say this is not transitive. Okay, therefore transitive is not true. So within these three conditions, reflexive is not true, symmetric is true, transitive is not true. Then how about the equivalence? It is not an equivalence relation. Okay, so fourth one, R is not an equivalence relation. That's all. Okay, clear? Now 8th question. Here the question is, let A is equal to A B C. Set of all the three elements A B C. What is the equivalence relation of smallest cardinality? Cardinality means number of elements. It's nothing but number of elements. That's all. Okay. What is the equivalence relation of smallest cardinality on A? So second case, what is the equivalence relation of largest cardinality on A? So here, by using these three elements, we can write one relation which consists of minimum elements. That should be an equivalence one. Okay, and like as we can write relation which consists of maximum number of elements. That should be an equivalence relation. That only they are asking here. By using these three elements, what is the minimum number of elements to say it is an equivalence relation? That's all. Okay. Now the first case, R is equal to A B B C C is the smallest cardinal, is an equivalence relation. R is equal to AA, BB, CC is an equivalence relation because here all are repeated elements only. Okay, the elements are paired with the same elements itself. So this is reflexive. and the pair A comma B is not here, then it is symmetric. Then like as AB, BC also not here, then it is transitive, then it is equivalence relation. So for this equivalence relation, how many elements are inside the relation? How many elements means how many pairs here? Okay, 1, 2, 3. 3 pairs are here. So n of R is equal to 3 is the smallest cardinality. Smallest cardinality. Smallest cardinality. Smallest cardinality. Okay. The second one, R is equal to the largest cardinality means write in cyclic order. Take first element, write pair with all the 3 elements. Take second element, write the pair with all the 3 elements. Take third element, write the pair with all the 3 elements. That is AA. Here the relation is from the set A to the set A only. Then the next pair should be A comma B, then A comma C. A is the first element. With the first element, we wrote the pair AA, AB, AC. Okay, now it is completed. Then start with B now. B, A, B, 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 C. Now the pairs which are started with B is completed. Then start with C. C, A, C, B, C, C. Here, reflexive is true. A, B, B, C, C are here because in the set 3 elements are there. Then the 3 elements pair AA, BB, CC are here. Suppose in this 3 value AA, BB, CC, if any one is missed, then it is not an reflexive. Okay? If 3 elements are here, all the 3 elements should have the pair with the same value. Okay? Then it is reflexive. Here it is reflexive. AB, BA, AC, CA. Okay? Then BC, CB, BA, AB, CA, AC, all are here. Okay, then is an equivalence relation. Is an equivalence relation. Here the n of R is equal to 9. Largest cardinality. So by this sum, okay, by this sum we can come on conclusion. Okay, if n of A is equal to n, if n of A is equal to n, then number of elements if n of A is equal to n, if n of A is equal to n, then for equivalence relation, first case, smallest cardinality, it should be n. Okay, largest cardinality, smallest cardinality, largest cardinality is equal to n square. This is one conclusion. Okay, if A has the n elements, by using these n elements, okay, we can write equivalence relation, but in that 2 different method of equivalence relations we can write. One is about smallest cardinality. Here A has 3 elements. Here we wrote a relation which consists of 3 pairs. This is an equivalence relation. Here A has 3 elements. Here we wrote one relation which consists of 9 elements. That too an equivalence relation only. So this is a largest cardinality number. This is smallest cardinality number. This is one conclusion from this sum. Okay.